At the base of the spatial stack, formats like GLTF and Universal Scene Description define geometry. Above that, the runtime layer uses interfaces like OpenXR to render displays. Next, the semantic spatial layer uses reality modeling language to share blocky spatial representations. To move data, the spatial messaging layer uses pub-sub protocols like spatial DDS to route bytes in real time. In parallel, standards like decentralized identifiers and verifiable credentials verify identity. None of these carry permissions between entities. Universal Manifest rides above the data fabrics and alongside identity standards as a portable envelope, carrying the exact permissions for entities to interact securely. When we discuss spatial computing, it is easy to default to the image of human avatars portaling between virtual worlds, but that specific use case represents only a fraction of the wider reality. The actual spatial computing problem is one of scale and intersection. We are engineering for an environment where countless entities encounter each other in real time. These encounters happen continuously in the physical world. A smart home device pings a phone, two autonomous vehicles ping each other, an AR headset analyzes a press. They happen in mixed and virtual contexts as well. An avatar steps into an entirely new virtual domain. A digital access door scans an approaching guest, or a newly deployed drone securely merges into an automated swarm. Universal Manifest is engineered specifically for this level of scale. It provides the necessary context and strictly bound permissions for any two entities that meet in space, whether they are hardware, software, or human. To see how this architecture functions in practice, consider a standard industrial scenario. A maintenance technician walks onto a factory floor wearing an AR headset and approaches a robotic press. That robotic press, despite being a stationary machine, carries its own actively updated Universal Manifest, originally issued by its manufacturer at installation. Looking at this diagram, we see the headset's manifest on the left and the machine's on the right. The machine's manifest holds a subject identifier, a safety rating, and a critical maintenance history facet, a sequence tracking previous service calls. On the left, the technician's manifest contains their specific identity claims, including a specialized maintainer credential bound by strict scope parameters for this exact site, equipment class, and working shift. As the two entities meet, they execute a bilateral exchange. Both sides simultaneously evaluate the other's manifest, checking consent rules and verifying credentials in real time. There is no negotiation down to a single document. Both read exactly the facets explicitly permitted. Some data remains strictly off-limits. The machine's manifest contains a proprietary internals facet, but it is sealed, encrypted solely to the manufacturer's keys. The technician's headset records that the facet is present, but it cannot read it. Because the technician's maintainer credential is valid and in scope, the machine's local controller completes the evaluation and physically unlocks its service interface. Trust in this environment is achieved because both entities generate verifiable receipts. Each side possesses cryptographic proof of exactly what was authorized, what was read, and what remained sealed, enabling necessary access while protecting proprietary trade secrets. Now let's remove the human element entirely. Consider two autonomous vehicles approaching a smart city intersection. Crucially, they are managed by completely different operators. As they approach, both vehicles continuously share their perceived reality data over a spatial pub-sub fabric. We can see the division of labor clearly in this visualization. The spatial messaging fabric below handles the heavy lifting of moving the raw bytes. Hovering above, the Universal Manifest envelopes act as the active permissions layer, dictating what those bytes mean. Inside those envelopes, each vehicle carries a specific sharing policy facet. These policies define the exact broadcast rules and consent requirements for the telemetry they transmit. Vehicle A's sharing policy evaluates Vehicle B's identity and actively permits it to read high-level obstacle detection facets. This ensures critical, localized safety information passes fluidly across operator lines. At the exact same time, Vehicle A's proprietary telemetry, data destined for its own operator's internal analytics pipeline, remains strictly sealed and invisible to Vehicle B. The architectural advantage here is that these two vehicles successfully execute a secure cross-operator data share without any prearranged bespoke integration between their parent companies. Scalable machine-to-machine networking cannot rely on rigid point-to-point connections. It requires a portable permissions envelope that allows entities to safely navigate dynamic encounters on the fly. This brings us to how Universal Manifest fits within the broader, active spatial computing ecosystem. As this constellation map illustrates, Universal Manifest is strictly a composition layer. It does not attempt to replace the asset, identity, or fabric standards that the industry already relies on. Instead, it references and carries them. When we look at spatial messaging protocols, Universal Manifest rides entirely above transports like Spatial DDS. DDS efficiently moves the bytes, while the manifest securely manages the permissions envelope wrapping those bytes. For semantic layers, Universal Manifest carries the precise entity identity and consent context required to operate within the shared reality spaces defined by the reality modeling language. In the realm of content discovery, Universal Manifest provides the necessary personalization context that frameworks like Web of Worlds utilize to surface relevant nearby experiences. And crucially, the framework remains entirely agnostic to identity standards. It natively accepts whatever protocol the issuer prefers, gracefully carrying decentralized identifiers, verifiable credentials, or OMA-Trust attestations. Universal Manifest makes no attempt to absorb or rewrite these independent projects. Its sole function is to solve the glaring permissions and consent gap. A highly functional spatial ecosystem demands specialized standards that excel at their distinct jobs. They are unified only by a standardized cross-domain handshake that respects permissions. The core challenge of spatial computing remains. As digital and physical environments merge, entities are constantly colliding across systems built in isolation. The solution is to move away from bespoke, faith-based network integrations and replace them with verifiable, standardized bilateral handshakes. Positioned directly above the spatial messaging fabric and working alongside established identity standards, Universal Manifest acts as the critical bridge connecting physical and virtual realities. This overview establishes the foundational mental model for the spatial computing community. To see the specific mechanics of this specification in practice, we have prepared deeper, sector-specific operational breakdowns tailored for engineers and developers. For physical world applications, you can explore detailed walkthroughs on industrial AR workflows, autonomous vehicle network interactions, and localized smart home device environments. For virtual and network routing applications, we offer extensive documentation on avatar portaling, automated robot and drone deployments, 6G sensing with rigorous bystander consent, and spatial content discovery protocols. Select the specific domain branch most relevant to your work to see exactly how Universal Manifest solves your immediate cross-platform engineering challenges.